talk to you about my latest project, which is the development of Phasor as FLIM, which stands for Spectral and Fluorescence Lifetime Imaging Microscope. So essentially, like starting from the basics, a fluorophore can be approximated to a two-stage system where you have two electronic states, S0 and S1, S1 being the excited state, S0 being ground state. Upon absorption of a photon of a certain wavelength, the system can transition to one of these vibrational states of the excited state, and then relax in a series of non-radiative decay. So each one of these transitions will not result in an emission of a photon. Then after some time, the system will transition back to one other of the substates of the ground state, and this transition between electronic states results effectively in an emission of a photon. As you can see, the energy difference between these jumps and this jump is shorter in this case. That means that the photons that are emitted have a lower energy than the photons that are absorbed, and therefore the color of the fluorescence is more redshifted than the wavelength that you use for excitation. This is very useful, of course, in fluorescence microscopy because it allows to separate the light that's used for excitation from the light that's coming from the sample. So this process has two main properties, one being the emission spectrum, so the distribution of wavelengths that can be emitted by the fluorophore, and the fluorescence lifetime. So the fluorescence lifetime is the distribution of the time that it takes to from the excitation to decay back to the ground state. This is described by an exponential, typically a single exponential distribution, and the constant of this fluorescence decay, this exponential decay, is called fluorescence life. It's basically the time, more or less the time that the fluorophore spends in the excited state. So this is all very interesting, but all of this information is actually lost in normal microscopy settings, right? So all the fluorescence emission is simply integrated by the detector, and we don't have these layers of information that allows us to know more about what the fluorophores are doing. So some system has, as you also have seen this throughout this workshop, have with the dedicated electronics and excitation modality can actually detect the fluorescence lifetime at every pixel. Some other system, instead of a detector, have a diffraction grating, displays the light by color, and then each different very small emission, spectral emissions, are collected by a detector array. So this detector will collect the light coming from the blue emission, and this detector will collect the light coming from the red emission, and you will effectively have a spectrum, an emission spectrum for each of the pixel of your image, right? What we did was basically taking a detector of this sort and making every one of these detectors capable of acquiring the lifetime information. This was done with the new multi-channel digital frequency domain implementation based on FPGAs that was done in collaboration with FLIM labs. So now, so when you think of an image, you think of a bunch of pixels, and every pixel will have some value, right? Ranging from 0 to whatever. Actually, we don't have one value, but we have a matrix in each pixel where it describes both the emission spectrum in this direction, sampled in 32 points, and the fluorescence decay sampled in 256 points. So now, each one of our images is 256, so let's say by 256 by 256 by 32. Now, this poses a problem because effectively what we're doing is for every image, we're actually collecting almost 7,200 images, right? So it's a lot of data. And since we don't like to settle with whatever, let's process it in like the hours. We want to have also something on the computational side that allows us to see whatever we are acquiring in real time. So how do we do that? We do it with the Phasor approach, of course. So let's skip a little bit the mathematics. You must have seen it 1,000 times in this workshop. But basically, let's go to the pictures. So what you see here is what happens when you transform a lifetime decay into the Phasor. So if you have a very sharp fluorescence decay, it will be here on the far right side of the Phasor plot. And then the longer the fluorescence lifetime becomes, the more this will shift along this universal semicircle until you will have something that practically flat that will be exactly in 0, 0, right? This is what happens with when you transform that. Why is this advantageous? Because you have to imagine that you have one of these curves for each pixel of your image, right? Once you transform it, you just have two coordinates and you can visually evaluate what is the lifetime in each pixel of it. You can literally color code according to the position along this circle, and you'll have just one lifetime image. And you can sort of see like, oh yes, we have one population, two population, three population, combinations and so on. So speaking of combinations, what happens when you have a combination of two lifetimes, right? So when you have a combination of two lifetimes that has a phasor that is in A or in B, the phasor of their combination will be placed along the line connecting the two pure points. So the phasor position of the black curve will be somewhere along this line, right? The position along this line depends on the relative fraction of the two, the photon contribution, let's say, of the two decays. So if you have 100% photons coming from B, it will be B. If you have 50% of the photon coming from one or from the other, it will be exactly midway. And if you have all the photons coming from A, it will be exactly in the phasor of A. That's also useful because you can visually immediately evaluate whether your decay is a single exponential decay or if you have multiple decay within the same curve. So if you have the species overlapping, for instance, which is typically the case when you have imaging and you label multiple components, you will have a phasor that's not on the outskirt of this semicircle, but will be inside. For the spectra is something similar, although there's much more space in the phasor. So you can virtually occupy any space with spectra. And here is more convenient to describe it in polar coordinates. So in this case, you will have the angle. As you can see, the angle is higher, the more redshifted is the spectrum. So blue spectra will be narrow, will have a narrow angle, and then green, orange, red, and so on. The phasor transformation also encodes the width of the spectrum. So the broader spectra will be shifted more and more towards the center of the phasor plot. As for lifetime, you can effectively mix up to 3 components using the first harmonic. And as you can see, with different contribution from the different spectra, the final combination will be somewhere inside the triangle that's described by the pure components of the spectra. So having the 3 spectra, you can immediately do a spectral unmixing in real time and without any which is very computationally efficient and actually works better than most unmixing methods. So why do we care about this? Right? We can do unmixing, we can do fitting, we can do whatever. So there's a reason why we go through all this trouble. It's because actually, if you take a look at what the fitting does and what the Phasor approach does, you will see that the Phasor will have a much lower bias when you have a very low number of photons. Why that is? That's because you can imagine, so we're sampling the lifetime, for instance, in 256 points, right? So here in this regime, we have 10 photons, right? So that means that we have way less than 1 photon per bin, right? Plus all the other effects that can degrade your signal, right? So the fitting starts giving you random numbers with a lot of error, but mostly we don't care much about the error as much as the bias. So you want, let's say, if you have, like in an image, right? If you have a lot of pixels with very few photons, you want that the average of those pixels actually give you the real result, right? With the fitting, it doesn't. That's the main thing. And also, it's much faster computationally to acquire, to process the data with the Phasor approach than with fitting. And by faster, I mean thousands of times faster. So it takes seconds instead of quarter hours. So to summarize, with the Phasor, we can achieve the same precision as the fitting, sometimes higher. We have a negligible bias, even for very low number of photons. That's important to not overestimate some lifetimes in favor of others. And then the time it takes to process an entire image, instead of 1,000 seconds, we can go below a second with GPU acceleration, or just 4 seconds with the CPU, which is more or less the frame time that we use for this acquisition. Of course, this is just on the detection side. So if you have a microscope that can perform like tiling and something like this, you can look at very large field of view and have not only the normal intensity image, for instance, but you also have the details that come out from looking at the lifetime images and from looking at the spectra. So if you take a closer look, there are some structures that can be discriminated by lifetime, but some that have a very similar lifetime, like this guy and this guy, and have a very different spectral emission. So that's very useful for classification, because that's why I call it multidimensional microscopy, because it gives you more layers of information than simple fluorescence intensity. Now, this is blind. Let's say we just look at the things. It has pretty colors, so we're happy with it. But we can also do something more in depth. For instance, we developed on this base a method for doing blind unmixing of both spectral and lifetime information. So let's take a look, for instance, at this cell. So this is a cell labeled with 3 organelle-specific fluorophores. And once you process it with our blind unmixing method, you actually split the signal coming from what is a tubulin marker, mitochondrial marker, and lysosomal marker, even though you have basically a perfect overlap of all 3 signals in every pixel. Right? But not only, because the unmixed images are FLIM images. So we can do in one single shot 3-color FLIM, for instance, no matter how heavy is the overlap. This is just to show that the single fluorophores and the lifetime from the unmixed fluorophore is exactly the same, as well as the spectral emission. And this sample is actually quite challenging, because the difference in emission spectrum between the mitochondrial marker and the lysosomal marker is just 14 nanometers. Then we want to see how much this works in, let's call them photon-starved images, right? So What we did was artificially decreasing the number of photons and see how well the method performs, even when you have very low photons. So we went down to an average of 0.6 photons per pixel per dye. And then we can see that both the spectra and the lifetime is still recovered pretty well, even when one of the fluorophores, in this case this one, is much brighter than this fluorophore here. Again, here we have a complete overlap of the three signals. So why do we care about photon-starved situation? So what we also did was looking at biosensors. So the problem of biosensors is that they're constructed like this one. This is a methylation biosensor. So you have a histone, HP1, which is responsible for the methylation of histone H3, and the FRET. The problem in this case is that since both the histone and the HP1 are actually do something in the cell, it's not an inert probe. So the problem is that if you overexpress this sensor, you end up with a chromatin that is artificially more compact than normal chromatin. And you don't want to do that. You want a method of measurement that doesn't affect whatever you're going to measure, right? Problem is that this is what you get when you look at low expression of this biosensor. You basically can't distinguish anything, except when once you apply a mixing and you evaluate the FRET with spectral FLIM, you can actually get a really nice separation between the condition, as you can see here, as opposed to here. This can be also applied to 3D cultures. In this case, we labeled a breast cancer spheroid with two dyes, Nile Red and JC1. Both of them have two, typically emission spectra. One, the Nile Red has a spectrum that localizes more in lipid droplets, one more in membranes, and JC1 labels the mitochondria in green and active mitochondria, meaning hyperpolarized mitochondria, in orange. So we have four spectral components that we characterize separately. And then we can use this information to a mix of four images, each of which is a FLIM image. Then we did a bit of mix and match. So we did the GP based on the spectral information between the two channels of the Nile Red to look at the lipid droplet concentration. Then we did the GP for the JC1 to look at the distribution of mitochondrial activity. And then we used the two lifetimes of the lipid droplets and membrane to look at lipid composition and membrane order. And we could map all of this at the single cell level over the entire sphere. With tiling, you can do the same just by looking at the lifetime or the spectral emission, and you can go over large fields of view again, millimeter squared, and you can go to single cells. As you can see, the intensity doesn't tell you much, but you have a nice difference in lifetime information and spectral information between the center and the periphery and the invasions, what is going to form metastasis later on of the spheroid. So this is a very powerful method. It's fast, it's real time, and it gives you really a lot of information about what's happening in your system.